automation engineering team, and we are paid to code to break code. So today we are going to try and break some popular beliefs or assumptions about the distributed system and how we think that they are reliable, but they might not be. So today we'll talk about the distributed fault injection testing, and we'll see how we do it at Flipkart. So that brings us to the agenda. So we'll see why fault injection testing is important and why we need it. Then we'll look at some of the false scenarios and fallacies, which we think is true, but it might not be. Then we'll look at the high-level architecture of the framework which we have developed to do such a testing, which we call DiFIT framework. And Shwet will talk about the tech stack of the framework, and then we'll open the house for question and answers. So why exactly do we need fault injection testing? So if you look at today's web world, how the projects are architected, we are always talking about a distributed system. And there are so many services involved, and they talk to each other in sync or async manner. And there are message queues involved, there are infrastructures involved, the databases are there. So it's a complete distributed system, and the faults can be at one or many points in such a system. So if you take example of Flipkart as such, so we have something called supply chain in Flipkart, which is the backend. There are around 20 services, 20 different services, and each service has 4 instances, and they run under a load balancer. So what we are looking at is around 80 services running together, talking to each other in sync or async manner, and then there are infra pieces involved, like memcache, databases, and all of these services talk to the databases which are at a remote location again. So that is the level of complexity we are talking about. And in such a system, if a fault occurs, it can be disastrous. For example, if the message queue system goes down, our message queue system every day processes around 75 lakhs to 1 crore messages. That's a huge number. And if that system goes down, the supply chain goes down, Flipkart's business goes down. That's the impact we are looking at. So although we think that the distributed systems are good, they're reliable, but we have to agree to the fact that even distributed systems can be very, very unreliable. So, and this is not a new notion. Some guy called Peter Deutsch and later James Gosling, in the 90s actually, they were talking about these fallacies. And they say that the network is not reliable, latency is 0. So these are the things which people assume they are saying, which we shouldn't be assuming. For example, we say network is reliable. Yes, if you look at hardwares today, the switches or the hardware load balancers, they are very reliable. They have less mean time between failures and all, yes. But Mr. Murphy is always there. He'll make sure that it goes down when you least expect it. So that's what we are looking at. So suppose a big business day is coming up, and that day itself the network goes down. What do you do? Similarly, the other fallacies, latency is 0, bandwidth is infinite. Again, we say, yeah, bandwidth is growing at a fast pace. We are talking in terms of Gbps and all. But we are also talking about videos and music being shared and passed around. So similarly, the other ones, and they are pretty much self-evident. The network is not secure, the topology does change, and yep. So based on the previous 8 fallacies, what we have tried to do here is we have tried to divide the fallacies into different kinds of faults which can occur. So we call them the application faults or the system faults. So if you look at the application faults, we are saying that if we have a service running, the target service or a cluster, everything can go down. Target can go down or the entire cluster can go down. If a message is intended for a target, what if the target is not up? We have high availability scenarios. We say that our service is highly available. We do a best effort. If it goes down, we try to bring it up. But are we actually doing it? We don't know. Similarly, we have system intensive operations like garbage collection, etc. And then there can be faults at network level or the disk level. For example, if the disk is full, do we actually do the rotation of logs or things like that? Or are we clearing up the DB? So these are kind of the faults which we want to explore. So how exactly do we test for faults? We'll take example of, say, just two services talking to each other, service 1 and service 2. And we say that what if service 2 goes down? So in this case, if service 2 goes down, something which was intended for service 2 wouldn't be received. So we want to see if service 1 gets the expected error back, or it behaves the way it was supposed to be in a fail-safe manner. And how exactly would you test it? Manually, if you try to test it, you would do, okay, first of all, you need to find the command which you need to execute to stop service. You need to log into the system, for example, SSH or remote login or whatever. Run the command, then do the operation which will generate a message for service 2, then verify whether the message came back with the right error code or not. That's the manual process, but there are some challenges involved again. First thing first, yes, you have to know the commands. So we say that, okay, bring down the service. That can be a fairly simple command, but what if you need to inject a network fault? That's not fairly simple, and you just can't go and say that, okay, remove this socket or that socket or things like that. And there's one more thing, exactly. So if we say that we want to bring down the network, the service is running on a VM, virtual machine, and you bring down the network, how do you access the virtual machine again to bring up the network? You don't have an access to it. So the only solution left to you is go and restart the virtual machine itself, which is not a good solution. And with any manual testing, repeatability takes a hit. And so if you have to do the same thing for service 3, service 4, and so on, you just can't do it. So that brings us to a thought that what if we have something very simple which we can just call as a HTTP endpoint that does this job for us. For example, if we have, say, a put method which says that stop service 2. It just takes the payload, it has the host in here, says that, okay, go to this host and stop the service. And then it gives me back the responses that, okay, I could stop the service or I couldn't. It'll be just very simple for me to use this, and maybe I can use this in my automation as well. So with that, we'll try to look at the architecture of the framework which we have developed around such an idea. And before that, we'll see how a typical order flows, typical flow of order inside an e-commerce company. So firstly, we have tried to show a very stripped down version of the supply chain which we have. So we are saying that, say service 1 is order management system and service 2 is the fulfillment system. And they are talking to each other via a message queue. The message queue here is taking messages from order management system and takes it and then passes it on to fulfillment. They don't want to talk synchronously. And the order comes from website, and it first comes to the order management system, and then it passes along. Supply chain can contain more systems like payment, warehouse, and stuffs like that. So that's the flow. And what all can break in such a system? So the failure points can be at the database level, which you have tried to show in this yellow cylinders. So the database can be down or the database can be full. We can have network level faults, as I was talking earlier. There can be packet drops as well. There can be, the network can be choking. The message queue can fail. Message queue can be running in a highly available mode. So we have this master and slave. So what if the master is down? Does the slave work as expected? If the slave is down, does it come up automatically? Those kind of scenarios. And the kind of scenario which we were looking at in the previous slide. So what if the services itself is down? So we'll take example of fulfillment being down here. And what happens if fulfillment is down? So our test step would be to actually verify whether the message which was intended for fulfillment, instead of going to fulfillment, does the message queue puts it into a retry queue or not? So our message queue will actually try, so the retry queue's job is to try again whenever the service comes up. So we have to see whether it goes there or not to test it again. As I was telling earlier, we'll go there and stop the service, then create an order maybe from website or order management system, and then let it go on till the retry queue, and then go to the retry queue and verify if it is there or not. So we thought, instead of doing that, why not have an agent, the DiFIT agent, which is sitting on this service, which can take commands remotely. So there can be an external controller, which also is running an agent itself. Suppose you can give one, say a command line argument, command line in the CLI, you can say that, okay, stop fulfillment service. It knows where fulfillment is there and it goes and stops the service. So, okay, this kind of system can be a little bit tricky to use for everyone. So we thought, why not have a RESTful interface around the controller, which can be used by any kind of XUnit framework. For example, JUnit or TestUnit or RUnit. Currently, we are using Ruby. So it can be used by any kind of framework, and we can give HTTP requests, the kind of request which we were seeing earlier. And it can take this request and say fulfillment that, okay, stop it. And because of this agent, and we have the server and the agent can very well be on any of these systems, be it 1, 2, or many other systems. And it can be sitting on the message queue system, or it can be sitting on the order system or the database system, and it can give commands to stop or inject faults into that system as well. Now Shwet will walk you through the tech stack, and over to Shwet.
Thanks, Rahul. Good evening, people. Okay, after the architecture, let's move on to the DiFIT stack, and let's see what actually is DiFIT and how actually we built the agent and the server. So when we started working on this, we wanted from the architecture, it's pretty obvious that we have an agent and we have a controller that we are trying to control multiple agents through. So what we wanted was a simple way to communicate between the servers and agent, which is simple enough and highly reliable. So for that, we came up with the Staff. Staff is an open source project developed by IBM, and it actually allows you to create a P2P system, peer-to-peer network, where you can actually control or manage your systems through one place, and you can execute any command. You can remotely execute ls, it will get the response back. So the whole communication is taken care by the Staff here. Moving to the agent, on top of the Staff. So Staff gives you the basic things, and the communication part, that is all. But how do we actually write our own custom things? How do we actually inject faults? So for that, we have written DiFIT libraries, which are basically jars, which give you capabilities to inject faults in the system. So let's say you have an application and you want to start and restart. So we have dropped jars, which gives you custom commands to do that. So if we look at the DiFIT libraries, we have so these jars give you operations, where operations could be any of these: module operation, some network operation, infra operations. So module operations are basically if you have some application running, you have some service running on a machine, and you want to manage it. So those come in module operations. Network operations. As Rahul was telling, you want to bring the network interface down. You want to choke the network. How will you do it? So all those operations go into the network. You might be having DB. You might be using cache server. So to manage all those things, we have given infra operations. But having said that, these are the operations. These are not the only things that are capable, that our agent is capable. Let's say if you want to add some new functionality, let's have an example. Suppose we have an application and we have written some module operations to inject fault. Now tomorrow we want to move the applications behind our load balancers. We have multiple instances and then we want a load balancer in front of it. So the scenario totally changes here. The way you inject fault at the application level is different than the way you inject fault at hardware load balancer level. So DiFIT actually gives you a template which is kind of a fill in the blanks. You tell the DiFIT how to inject basically some simple commands through which you will inject the fault, and then package it, drop it on the server, tell the server, deploy it on a particular agent, and your agent is now capable of handling the new way to inject the fault. So That completes the agent. If we move to the server, so server also has the staff. At the bottom of the stack, we have the staff which actually taking care of the communication part. On top of this staff, we have created DiFIT APIs, which are basically Java APIs, which give you a control over the custom commands that can be executed on the DiFIT agent. It gives you APIs, which you can directly use in your Java code or on command line to execute those commands or inject the fault in the system through. So if we look at the system, this DiFIT agent coupled with DiFIT API staff in itself is a complete self-capable system. It gives you a command and option or plug it in your Java code to use it. But as Rahul was saying, wouldn't be it better for an end user to have one HTTP endpoint, REST endpoint, where I can just hit, send some payload, and my execution is done. The way I want the fault injection, it's done. So that's why we added one more layer on top of the DiFIT APIs. That is our REST interface. So REST interface gives us a neat and clean endpoint. To the end user, you don't need to know how actually the fault injection is happening. You just need to hit one endpoint with a payload. Other than giving a neat endpoint, it actually allows you, now you have a server. So you can deploy at one central place. The end user doesn't need any code or anything. He just needs a REST client or a browser to hit the server. That's it. One more capability, one more property of the server is, if you deploy the whole system into an org where you have like hundreds of agents running and you have server. So one of the key requirement would be to know, for an end user, he has to know what a particular agent can actually do, what all features, or if I want to manage, if I want to add some more capabilities. So management of the agents, that is also the part of the server. So moving ahead, let's see one of the scenarios that Rahul was talking about, how we actually automated that scenario. So this is a Ruby code and this is a test unit test case. We have like any typical test unit test case, we have 4 steps: setup, business flow, verification step, and your restore. So as Rahul was saying, for the test to complete, you have to have fulfillment down and then try to create an order, and then you have to actually check whether that message for that order actually went to your retry queue or not. So in the first step, we are bringing down the fulfillment. As you can see, the stop payload, it contains the host and forceful option. So for our test case, we need the fulfillment to be stopped anyhow. That's why we gave the command forceful kill, and we've told where the host is running, and then we hit a REST endpoint, fulfillment stop with the stop payload. That's it, and your fulfillment is down. After that, we execute the business flow. We create an order. We find the order ID. We find the message ID for that order, and then we wait till the message actually is into the queue system. After that wait, we verify whether the message in the queue or not, and then we bring up the system back. So with this code, we came to the end of the presentation. These are the references. The fallacies which Rahul was talking about is the first. It's a paper actually by Peter Deuce. Second is staff. Staff is hosted on SourceForge. You can have all the docs and binaries from there. For the REST interface, we have used drop wizard to actually create the REST interface, and that is there. The drop wizard code.
All right, and we do believe that the best way to avoid failure is to fail constantly, and we do it using DiFIT. Questions? So you should get the proper error back. So we had seen cases where we were not getting the right error back. So it was very difficult to debug which service was actually down. And there are so many services down the line which are talking to each other, and finally some response comes back to the origin of the command.
That tells me,
that service was not returning back whether I'm down. It was just failing randomly. So that kind of testing can be done using this framework. No, it's a separate service. It's not on top of anything.
It's not on top of anything. It's a complete different agent that is running.
Staff is a very lightweight service which runs on the machine, and
we have created our own package with our own configurations and all, which you can simply deploy, and that's it. You have to just deploy. So it's basically our package. You can.
No, not exactly. I would say group of services. For example, our supply chain services are very similar. The way they can start, stop, or maybe they can go out of rotation or in rotation.
If you have a peculiar service that it's totally different, it's not like any normal application which doesn't follow the conventions, then yes, you'll have to write it. Otherwise, it is available.
So it actually does provide an interface where you can just say, okay, go and execute this command.
That's it.
But we have created abstractions around it so that it's easy to do it. You don't have to specify one entire command. And
so you've been talking about all the faults are complete unavailability of a service, right?
Sorry?
All the faults that you have been introducing is
Yeah.
complete unavailability, right? What about degraded mode? Like, let's say I make a call.
Yeah.
It's supposed to return within, like, what about 10 milliseconds? And it takes like a minute to return, right? Have you been able to inject faults of those nature as opposed to saying service completely unavailable? How does code behave?
yeah, actually that's in progress. We are talking about packet drops, for example. So we haven't done that, but we have some ideas how to do it. But yeah, that's under progress.
We can actually, for that, you can actually make your system, you can choke your network. So when you're saying 10 millisecond response is taking 1 minute, it's basically either your system is slow or the network is slow, okay? So if you choke your system, that we can do. If you choke your network, then you will get the late response, and then you can simulate that behavior, how the system is behaving actually in that scenario.
So if we can find a command or a set of commands which we need to do run to simulate that, we can very well do that.
No, even other than I will add to that. I will, for that scenario, I can open multiple connections. Okay, on that particular machines, multiple TCP/IP net channels I will open, so that when your request comes, it's basically a kind of DOS I will make on that system. Through that I can do through DiFIT, and so when your request comes, your request will time out because the network is choked.
I mean, yeah, if your network failure is what you're chasing, there is a command called just TC on Linux, traffic control. You can probably just look at that.
Yeah, could be. Yeah,
right?
yeah.
So
I mean, there are ways it can be done.
But sort of the larger question was, how much of emphasis is on degraded testing in degraded mode versus complete failure of subsystems?
It's there
That is the
actually.
larger
We are trying to look at both kind of scenarios.
No, so right now most of the emphasis on the complete broken systems. Anything else?
Thanks, guys.